Hello, welcome to the Vent Intelligent System for Temperature Adjustment, or VISTA, sponsored by Dr. QZ Sun. We, Group 34, are composed of Katia Brown, EE, myself, Alex Tatalias, EE, Luke Morrison, CPE, and Bella Polke, EE.
In many homes, there is an issue of one room being too hot or too cold if it is further away from the thermostat. This can lead to high power and energy consumption, and this is not only bad for the environment, but is also bad for your electricity bill. Some people may propose the use of a smart thermostat, and while this is an option, they are typically very expensive and difficult to install. In addition, those devices are typically very size-specific, which may inhibit consumers from being able to use them. And of course, some people might say to just turn on the fan or the heater. This solution is fine short term, but our system helps to alleviate the hassle of using outside cooling sources. If you have an AC, you want it to work at its highest potential so that you do not need additional cooling devices. In addition to this, our system helps to reduce security and health risks associated with fans and heaters, such as fire hazards and dust circulation. We wanted to create a solution to these problems, and that is where the Vista comes into play. Our device combines all of the traditional methods of air conditioning and combines them with smart technology to offer consumers a low-cost, reliable solution.
The main objective of VISTA is to create a semi-autonomous system that will decrease the loss and overall energy cost of a home or building by responding to sensor data. Thus, in a broad sense, the goals of the smart vent system include reducing energy consumption and autonomous functionality or remotely controlled capabilities. More specifically, the objectives of VISTA include opening and closing the vent louvers or slats autonomously, detecting and responding to room temperature, occupancy, and humidity levels, and enabling users to operate the system via a mobile device. These are the engineering specifications for the smart vent system, split up into hardware, power supply, software, and energy usage sections. The three demonstrable specifications, as highlighted, include a room occupancy accuracy of 90%, a response time of under 5 minutes in order to fully open or close the vent based on sensor indications, and a network range of at least 50 feet. Some other specifications, as shown in the table, include the lifetime of the device, dimensions, battery life, communication rate, etc., all of which work in tandem to create a product with sufficient parameters to suit the purpose of VISTA.
Hardware comparison and selection. In this section, we will discuss each of the different hardware components we chose for our project. There will be a comparison of different hardware technology and why we chose each specific one for our project. This is our hardware diagram. As you can see, there is one main PCB that communicates with the different sensors and takes the information from them to send to the mobile app. The MCU uses the Wi-Fi module to communicate this information within the app. To open and close the vent cover, there is a little bar on the side called a louver. This is important to note because we need a device that could interact with the already established mechanisms of an AC vent. We ended up choosing a servo for the mechanical component because we needed something to open and close the vent. This could be done with a linear solenoid, but would then most likely require two, and a similar issue was caused by the linear actuator. The servo also has the unique feature of rotational movement that the other components did not, making it the best fit for the VISTA system. Originally, we chose the FS90R servo as it has the widest rotational range. Originally, this seemed like a positive, but it ended up being an issue as it caused the servo to get lost in its rotations. Due to this issue, we discovered while testing, we decided to shift to the SG90 micro servo. This servo has the ability to adjust to a 90-degree angle and fully open or close the vent device.
In order to choose the controller type, we compared MCUs and FPGAs. After researching both options, it was determined that, like with many of the other senior design groups, FPGA capabilities really go beyond the need of VISTA. So although they have advantages such as parallel processing, reconfigurability, and quicker computation time, the simplicity and energy efficiency of the MCU, as well as its small size, made it the ideal choice for our project. Then the original MCU we chose was the STM32, mainly because we already had it and the capabilities were suitable for VISTA. However, we ended up switching to the ESP32 after getting advice from Dr. Weeks, mostly due to the fact that it has already established Arduino libraries that are applicable to many of our components, as well as the built-in Wi-Fi module.
When it came to temperature sensors, thermistors and semiconductors both operate on the same underlying principle, which is just that as a material changes its temperature, a known property like resistance or some other property will change in a measurably and predictable way. Infrared temperature sensors differ in their uniqueness that they just measure the infrared radiation emitted from an object as a result of heat and blackbody radiation. This serves to our advantage because our use case is going to be putting it right on an air vent, which the material-based sensors will only be able to detect the immediate temperature or the local temperature of the air right around it, whereas an infrared sensor should hopefully be able to detect the temperature from a further distance away, hopefully getting a more accurate reading of the overall room temperature and not just what's coming right out the air vent. When it came to picking the temperature sensor specifically, we really just had to take into account costs and the actual power draw. Additionally, the simplicity was a good factor in choosing, and the best candidate for all of these was the MLX 9061 series. It also happens to be pretty well documented in the datasheet as well.
The passive infrared sensor was chosen for its high accuracy, low power consumption, and different operational modes, the latter being the biggest plus of this type of sensor. The passive infrared sensor offers different operational modes such as low power and sleep. This is perfect for our project as we are trying to save on consumption wherever we can. The other two types of sensors, Bluetooth Low Energy and Thermocouple, were not chosen based on difficult integration with the system and low data rates. When deciding which type of passive infrared occupancy sensor, the Grove PIR sensor was the best choice for our application, for many reasons, including its wide detection range and low power consumption. Due to the complexity of a PIR sensor, the main two options we had were build out our own on a PCB daughter board or use a fully built-out PIR sensor. Due to the scope of our project and our project timeline, we decided to build our own. So we built out our own daughter board using the Grove PIR sensors datasheet as a guideline.
Vista uses a humidity sensor to detect and respond to humidity levels in a given space and therefore make changes to the vent slats to conserve energy or perform some sort of other functionality. The humidity sensor technology comparison included capacitive versus resistive versus psychrometric humidity sensors. As you can see in the visual representation, the capacitive humidity sensor works by using a capacitor, thus two electrodes separated by a dielectric material. Then humidity is measured by applying AC voltage between the electrodes, and the change in capacitance between those electrodes results from a change in permittivity of the dielectric material as it absorbs moisture. So as moisture is being absorbed by the capacitance increases. Resistive was a close second due to very similar features, but capacitive has high accuracy and stability, as well as quicker response and recovery times. And then psychrometric was not even close to being considered. The HIH 8120 humidity sensor was chosen over the others primarily due to its quick response time and suitable ranges for temperature and voltage operation. Additionally, the schematic, as shown on this slide, was very easy to integrate onto our main components board and left less room for possible errors. Choosing the power source included comparing several different batteries as shown in the table, as well as the potential for a wall connection. We ended up going with alkaline batteries over lithium ion, which was a close second due to the more environmentally friendly qualities, allowing for easy disposal, as well as the temperature resistivity. Alkaline batteries are overall a good choice to suit our needs based on the high energy density, allowing for long shelf life as well as the non-toxicity. When comparing the different types of alkaline batteries, AA batteries were small and lacked many of the necessary qualities. C and D batteries were very similar and better than AA. And then 9-volt batteries ended up surpassing the other options, mainly due to the small size and high voltage. Additionally, since Vista is meant to be a widely usable product, 9-volt alkaline batteries are a suitable choice due to them being widely available and commonly used as batteries because it's typically found in appliances like smoke detectors that are already in people's homes.
When it came to choosing regulators for design, the biggest criteria to take into consideration was efficiency and power loss. This is mainly because our device is intended to be battery operated and function long term, similar to a smoke alarm where you don't want to change the batteries too often. So with this in mind, the linear regulators are not a very strong candidate as they're inherently significantly more inefficient than a switching regulator in this case, and specifically a lower frequency or relatively lower frequency switching regulator will be the most power efficient of all the options. So because of that reason alone, we went with the switching regulator. When it came to picking the regulators themselves, the main thing we had to consider was we're going to be operating off a 9-volt DC battery, and all of our components are going to be running off of either a 3.3 or a 5-volt power line. Now, we did want to have a little bit of a cushion just in case we had to change anything down the line, and on that note, we also wanted to have a high tolerance for our max output current, which, as we're working with servos, we didn't know if maybe we need another one or a different kind, so just want to kind of cover our bases there. The final thing was that this was a tip from a former senior design student, but to find a regulator with a really high quality data sheet, specifically one that had like example placements and component values used for different configurations. And the one that just happened to fit this perfectly was the Richtech RT820 series. It also was not that expensive compared to anything else, so we chose that. As for actually manufacturing the PCB, there were a couple things to consider as far as manufacturers and technology and materials. The only real consideration we had, or place of worry I should say, is that since our device is going to be mounted onto a AC vent or potentially heat coming out of that vent, if it could just withstand thermal cycles. And really everything did, so we just chose Hazel lead free as it happens to be more eco-friendly than the others and also cheaper. And then we also just went with JLC PCB as our supplier. They're just the cheapest and have the quickest turnaround and good reputation online. There were a lot of avenues we could take as far as mounting goes. One of the requirements from Dr. QZ, our sponsor, was to make it as universal or one-size-fits-all and easy to install as possible. This helped narrow down our options a lot to really just anything that didn't involve drilling into the drywall or support beams behind it. Any super strong adhesive that might leave damage or require someone to repaint, anything of that nature. So the only real options left were to repurpose the existing machine screws that exist on most interior vents, and then also to ensure that it stays airtight. Our enclosure on top of the vent, we are adding a rubber adhesive to seal it against the surface.
Communication selection. In this section, we will discuss which communication technology we picked for our project and why it was the best choice for the Vista system. Wi-Fi ended up being the most suitable communication method for our device. It offers the ability to transmit large amounts of data quickly and offers a large communication range, which is important for user simplicity. Although Wi-Fi is not as quick of a communication method as some of the other wireless communication options, our system does not require real-time responsiveness, making these issues less prevalent. All three Wi-Fi modes offer valuable features for the system, but the Wi-Fi HT40 offers easy integration, high efficiency, and fast communication. Additionally, the HT40 mode is already built into the ESP module we are using, making this the most obvious choice for our device.
In this section, we'll be discussing the various software technologies and selections for this project. For the software of the Vista stack, we will have two components: the web application that will interface with the Vista device and the internal software. Both of these components will be required to work together seamlessly for the device to function properly. In this diagram, we are outlining how the device will determine when it is appropriate to open the vents to achieve the desired outcome. The Vista will need to be able to set the desired temperature of the room based on a number of internal variables determined from the device configuration process and from the Vista web app. These variables include the minimum temperature of the room, the maximum temperature of the room, the humidity, and the device mode, which are determined by the Vista web application. The diagram also showcases the series of events that will tell the ESP32 when it is appropriate to update the user interface. For example, when the device recognizes a change in internal temperature, it will report this change to the Vista, either through a back-end relay or through front-end direct communication. The web app will also receive information from the device configuration process, where the Vista device will set up a Wi-Fi access point, such as the device name and the Wi-Fi the user is connected to. For the Vista web application, we first determined the appropriate starting point to construct the web application stack. JavaScript was chosen to be the basis for the web application due to its popularity and extensive browser support. The React library was also chosen on top of this due to its extensive support and maintainability. It offers enough support for state management and UI updates to fulfill the purposes of the project and is easy to implement. The Vista web application serves simple purposes and will act similarly to controls for an AC vent at home. This justifies the usage of a simpler to implement front-end library for the user. For this project to function properly, the ESP32 will need to be able to send and receive HTTP requests from either the Vista backend or through a direct front-end communication. More will be discussed on this shortly. We decided to choose the Arduino web server library as opposed to the ESP asynchronous web server library to serve as HTTP request. This was done because the web server library already includes most of the functionality needed for this project, and also because we are utilizing the real-time operating system. Using free RTOS tasks to separate HTTP requests from internal logic means that the HTTP requests will already be working asynchronously in the background. ESP async web server would serve better in situations where the device needs to send and receive many HTTP requests in parallel. However, for the purposes of a smart controlled AC vent, this would prove to add too much complexity, so web server was chosen as opposed to it. One of the main objectives for our project was to ensure that the device is functioning regardless of external factors, such as an internet outage or from different browser configurations. In this case of an internal outage, the device prefers to establish a direct connection to the front end, meaning that if the React app is loaded into a browser, the device will continue working so long as a Wi-Fi connection is still established through the local area network. This practice is common in IoT applications where it is important for the device to be able to continue working and responding to user input in the case of a Wi-Fi or internet outage. Despite this, there arises complications where some browsers will restrict access to direct communications using local IP addresses. This problem gets solved with an external backend connection that exists for the ESP or the front end to forward HTTP requests that fail to connect. This ensures that the device will continue working during most use cases. In order to make this backup procedure possible, the ESP32 will report its current local IP address to the Vista backend and also the device data. The ESP will also regularly send a heartbeat message to the backend to indicate that the device is still connected. The frontend will check the device connectivity status to determine whether it should begin displaying a connectivity error if the device has not reported its activity recently. For the backend, we chose to use a Node.js server that will host various endpoints such as the heartbeat status, temperature, device mode, and other data points. The ESP32 will send its data sporadically in the case of a failure to connect via direct front-end communication. The backend will also manage a small SQLite database for storing this information, including the device name, IP address, device connectivity status, and these various data points. This diagram showcases the order of logic the ESP32 will go through when determining whether the device should configure itself to work with a backend connection or a front-end connection. The ESP32 will first attempt to initiate a connection with the front end, and if the connection is successful, then the device is configured to send all requests to the IP address retrieved from the database. This process will continue working until there is an interruption in the connection between the front end and the back end. This process will ensure that no matter what situation the user is in, the device will continue working properly. Free RTOS is included with the ESP32 libraries, meaning that the implementation is significantly simpler. Despite the lack of direct HTTP support that other real-time operating systems would offer, like Zephyr and Embed, the complexity of adding a new operating system doesn't justify the purposes of the project. The main reason for using tasks in FreeRTOS is simply to make parallel the HTTP send and receive tasks, so for this reason FreeRTOS works perfectly fine.
The system is split between 3 different boards, along with an externally mounted motor. Each board has a set of header pins for jumping between the boards, and the power board includes the holder for the 9-volt battery, and then outputs the 3.3 volt and 5 volt via jumper to the main board. The main board then has the temperature and humidity sensors, along with the ESP and a USB interface. Now there's jumpers to the power board, the actuating motor, and finally the PIR sensor board. And the PIR sensor board is used to detect motion and room occupancy, and it can be mounted externally to better angle or adjust for different room conditions. Place and route for the power board did not have too many unique design considerations. The main thing was that our switching regulator was a relatively low frequency, so we didn't have to consider any high frequency effects. As long as the coupling capacitor was placed close enough to the pin, it would effectively prevent any real ripple current, so there was no issue with that. Likewise, the PIR sensor board was also not too complicated with place and route. We just utilized a reference design from an existing dev board that happened to use the same chip for the sensor. Made things a lot easier just to use that as a reference, and it just outputs a simple digital on-off on the process data. And that connects to the main board via a set of jumpers. The main components board houses the ESP, which gets connected to USB via UART bridge. The temp sensor and humidity sensors are both then coupled to ground. As far as the actual place and route for these, most everything was just referenced off their respective data sheets. And then we routed everything from the daughter boards, from their jumpers to their appropriate place on the ESP mainly.
We have done a lot of prototyping and testing for this stage of the project. So far, all of the individual components work and we have assembled all of our PCBs. We are now just trying to get them to all work together. The main components board is almost fully functional. It is recognized by the computer, but is still having some difficulty interacting with the ESP32 module. The PIR sensor board is working and communicating with the computer, but the output is not correct. We're continuing to experiment with this board until we get it to work. The power board, which houses the 3.3 volt regulator and the 5 volt regulator, was not originally working correctly. The LEDs would flicker on and off, and sometimes it would output the correct voltage while other times it would not. So after some testing and probing, we realized this seemed like a physical error of the components rather than the board itself. So we resoldered the board and now it works as intended. The user interface has also been designed locally and will become integrated when the main board can recognize and communicate effectively with the ESP. We will continue to work on creating a prototype of the traditional ventilation system. Originally, we were going to implement a 3D printed ventilation cover to demonstrate our system, but we have pivoted to demonstrating the electronics of the system with window blinds. Once we have the AC vent prototype built, we will add our final prototype onto it to interact with it. This will make our prototype easier to transport and demonstrate. We will also continue in building the user interface and making sure consumers can easily use the device.
The budget for Vista so far has been about $428, which is well below our budget given by the project sponsor, Dr. Cusey's son. There will be some additional costs added soon for the physical vent materials as we start our build process, as well as small increases in cost of our components as we finalize getting all our PCBs to work and making sure that we have enough of the proper parts for that. But so far, our project costs are looking to be in a very suitable range. The work distribution between members is shown in this table. Most of the larger tasks like PCB design, ordering, soldering, testing has been split among the 3 EEs, which once again includes myself, Alex, and Bella, while the software side is being taken care of mainly by our CPE Luke. And then the specific tasks, mainly from the research portion of the project in SD1, are laid out under responsibilities, while once again the SD2 tasks have been more of a group effort. Here is our progress and completion plan. Currently we have a working power board and a semi-working main components board and PIR sensor board. Future completion includes testing and improving software once all the boards are fully operational, assembling the physical build of the project, integrating the electronics onto the physical build, and then otherwise testing and prototyping our product in time to debug as needed before the final review.